So design of one-way slab. In this video we will discuss, as we are discussed earlier, Ly by Lx greater than 2, we will consider it is one-way slab, whereas what are the data is given. So based upon the data only we will design the slabs. So for that, so in this problem, what are the data is given is clear span is given, that is standard support to support, inner support to support distance is 3.5 meter. Then support, width of the support is given 200 mm. Then live load is given 4 kilonewton per meter square. Floor finish 1 kilonewton per meter square. Then materials M20 grade of concrete, steel Fe415 steel is provided. So for that, characteristic compressive strength FCK equal to 20 Newton per mm square. For us, tensile stress Fy is equal to 415 Newton per mm square. So first we have to finding the what is the depth of the slab. So this is the slab. So we have to find the depth of the slab. So for that we have to go for a L by D ratio. So before going to the finding the depth of the slab, we have to know the IS 456 page number 37. So in that 23.2.1, the vertical deflection limit for all different types of support. So in our questions they provided the simply supported. So for that, so here basic values of span to effective depth for the up to 10 meter. Our span is 3.5 meter. So we can consider page number 37. Here simply supported 20. So L by D basics is 20. Then KT into KC. KT is nothing but the tension reinforcement modification factor. Then KC is modification factor for compression reinforcement. Here we provided the assume 0.4% of tension reinforcement. So 0.4% of tension reinforcement. So for that we have to refer page number 38. This graph. So in this graph they will provided the in the x-axis percentage tension reinforcement. In the y-axis they provided modification factor. So before refer the graph, we have to find the Fs value. So Fs value is nothing but the steel stress for the service load. So Fs formula is given 0.58 into Fy into area of steel required. Area of steel is provided. So for that, here area of steel is required is, we are assume 0.4%. So A is provided also 0.4%. So both are cancelled, become 1. 0.58 into 415. 415 nothing but the tensile stress. So we will get it 240. Here now go to the graph figure number 4, modification factor for tension reinforcement. In this there are 5 curves there based upon the Fs value. In our problem it will meet 4th curve, Fs equal to 240. So for that, for the x-axis 0.4, where it is touched here is 1.3. So KT value is 1.3. We have to refer for the compression reinforcement. Here we have considered compression reinforcement is 0. So percentage of compression reinforcement 0 for 1. So we consider as a 1. So KT is 1.3, KC is 1, L by D basic is 20. So 20 into 1.3 into 1, which is equal to 26. So now you can easily find out the L by D value. So L divided by D equal to 26. So we know the L value, that is 3.5. So D equal to 3500 divided by 26, which is equal to 134 mm. We will consider approximately 140 mm. So D is effective depth. For that, in order to finding the overall depth, assume clear cover 20 mm and the diameter of the bar is 10 mm. So overall depth is 140 effective depth plus dia by 2, reinforcement dia divided by 2, 10 by 2 plus 20, which is equal to 165 mm. So from the step depth of slab, we can easily find the overall depth of the slab. Step number 3, effective span. So we need to find the center to center distance from the one support to the another support. That L will be considered for the whole length. So there is a condition is the least value of clear span plus effective depth and center to center of support. So the value comes from these two conditions. So which is less, we will consider that, which is mentioned in the IS 456. So for that, clear span in our data is 3.5. Effective span we found it as 140 mm. So 3.5 plus 0.14 we convert in terms of meter. So 3.64 meter for the first condition, clear span plus effective depth. For the second condition, center to center of support 3.5. So this is the width of the support 200 mm. So one width we consider as the half of it. The center line is projected in the here. Another support we consider the center to center distance. So from here to here, the value is 3.5 plus 200 mm divided by 2, 200 mm divided by 2, which is equal to 3.7 meter. So now compare these two value. So this is the smaller one. So this is the least value. So L is 3.64 meter. Step number 4, we finding the load on the acting on the slab. So first of all, dead load. So dead load is nothing but the self height of the slab. So self height of the slab is overall depth 0.165 meter. Then we always design for 1 meter. So 1. Then unit weight of concrete is 25 kilonewton per meter square, meter cube. So that is 4.125 kilonewton per meter. Then live load, the given data is 4 kilonewton per meter. Then floor finish 1 kilonewton per meter. So overall 4.125, 4 plus 4, which is equal to 9.125 kilonewton per meter. So always we are designed for the limit state method. We convert in terms of factor load. So 1 times into our load. This is we call it as a service load. This is we call it as a ultimate load or factor load. So 1.5 times of service load, which is equal to 13.69 kilonewton per meter. So step number 5, bending moment and shear force. So since it is a simply supported beam, the formula for finding the bending moment, maximum bending moment, WL square by 8. So here W is ultimate load 13.69. Then here L is our effective span. L is 3.64. So 3.64 square. So 8, which is equal to 22.67 kilonewton meter. So shear force WL by 2, which is equal to 13.69 into 3.64 divided by 2, 24.92 kilonewton. So this is the factored bending moment, factored shear force. So next we have to check whether it is a under reinforced or over reinforced or balanced section. So for that condition is MU. If MU is less than MU limit, we are finding the MU limit. So for that, if the value is comes MU less than MU limit means under reinforced, that is a economical one. If it is MU equal to MU limit means balanced, then MU is greater than the MU limit is over reinforced. So it is an uneconomical design. So we have to redesign if it is comes. So now we will check limiting moment. The formula is MU limit equal to 0.138 FCK BD square. So 138 into FCK is 20. B is we always design for 1 meter, so 1000. So D is effective depth 140 square. So MU limit is 54 kilonewton meter. So now compare MU and MU limit. Our MU value is 22.67. MU limit value is 54. So MU is less than MU limit. So MU is less than is MU limit means under reinforced. So hence it is a under reinforced section, that is economical section. Step number 7, main reinforcement. So after calculating up to step number 6, you are going for a design of main reinforcement and as well as the distribution reinforcement. So main reinforcement, the formula mu equal to 0.87 Fy AST D in bracket 1 minus Fy AST divided by FCK BD. Since it is a under reinforced section, we have to use this formula. So mu value is 22.67. It is in kilonewton meter. So convert in terms of Newton mm. So into 10 power of 6. Then 0.87 into Fy is 415. AST is going to find it out. So D is effective depth 140. So 1 minus 415 AST divided by 20. So B is, we always design for 1 meter. So that's why we provided here 1000 mm. So D is 140. So after simplifying this equation, we will get the in terms of AST. That is AST is equal to 480 mm square. So we have to provide 10 mm dia bar for the slab. So spacing for between one reinforcement to another reinforcement. So that is 1 meter spacing. That is a 1000, which is equal to 1 meter. So we always design for 1 meter. So 1000 into small AST divided by capital AST. So overall reinforcement is 480. We providing single reinforcement. So 1000 into pi by 4 into 10 square. Pi d square formula, pi d square by 4 formula. So area of steel. So divided by AST, capital AST. So we will get the 164 mm. The spacing between one reinforcement to another reinforcement is 160 at least we have to provide. So adopt spacing of 160 mm. And since it is a slab, we have to provide alternate bars. One bar we have to bend like that, another bar will be provided in the flat. Since we have to maintain that overall thickness. So alternate bars are bent up at support. Next we have to find the distribution reinforcement. So distribution reinforcement we provided in the formula itself, IS 456. We have to, if we are using HOSD bars, we have to apply 0.12% of BD. In case of mild steel, we have to apply 0.15%. So now we are using HOSD bars. So 0.12% of cross section. So 0.12, it is a percentage. So divided by 100 into, we design for 1 meter. So 1000 into overall depth is 165. So we will get 198 mm square. So this is a distribution reinforcement. We will provide minimum reinforcement, that is 8 mm dia bar. So at 200 mm, 250 mm center to center distance. So next we have to check for shear stress. So shear stress, we have to compare the tau C value and tau V value. So tau V value formula is VU by BD. It is provided, it is available in the IS 456. So V is 24.92 kilonewton. We convert in terms of Newton. So into 10 power of 3. So B is 1000, D is 140. So 0.18 Newton per mm square. So to find the tau C, we need percentage of tensile reinforcement. So formula is 100 AST divided by BD. So 100 is percentage. So into AST is 480 mm square divided by 1000 into effective depth 140. So 0.17% of tensile reinforcement. So we have to refer IS 456, page number 73, table number 19. So this is IS 456, page number 73, table number 19. They provided the formula 100 AST by BD. So here the PT value is given, concrete grade is given. So since our design problem is M30 grade of concrete, our PT value is 0.17. We have to interpolate between 0.15 to 0.25. So we will provide approximate value, that is 0.29. So 0.15 value is 0.28. 0.220 value is 0.36. So we have to interpolate for exactly. So now we have a approximate value is 0.29 Newton per mm square, because our tau V value is 0.18. So always it is greater than the tau V value. So tau C is greater than the tau V. So shear stress is safe within the limit. So no need to worry. So we provide the 8 mm dia bar itself, it is provide the safe. Next step number 10, check for deflection. So we have to compare maximum L by D ratio and actual L by D ratio. We found it out. L by D maximum value is 28. L by D actual 3640 by 140, which is equal to 26. So here 26, so 28 greater than 26. So it is also safe. So hence deflection of slab is safe within the safe limit. So CST is also safe, deflection also safe. So we design this one-way slab is safe and economical one. The final step is reinforcement details. So this is our slab. So slab overall depth is 165 mm. This is support. So support with this 200 mm. It's a clear span 3.5 meter. So this is your slab reinforcement. So here red color highlighted one is main reinforcement. So main reinforcement we designed as 10 mm dia bar, 160 mm space, center to center support. So in case of main reinforcement we are providing like that. So another main reinforcement, the distance between one reinforcement to another reinforcement is 160 mm. So when we are see from the top, so then only we can easily see the main reinforcement spacing. Whereas if you see from the elevation point of view, cut section, so we can easily see the distribution bars. So these are the black color dot is represent as a distribution reinforcement bar. So this is the 8 mm dia bar, 250 mm center to center spacing. One reinforcement to another reinforcement, the spacing is 250 mm center to center support, distribution reinforcement. So the effective depth up to top of the layer to up to reinforcement 140 mm. So then we always bend some 0.1 L length of from the support. So that length is 360 mm, either support from the left and as well as the right. So we have to bend at the distance of 300 mm at here. It will give for some proper height for the slab. So these are the detailing of reinforcement of a one-way slab what we have designed so far. So thank you all.